Copper inductor steel tube. Steel tube is heated in the inductor. The task is to find the temperature rise after 10 seconds of heating. The initial temperature is plus 25 degrees Celsius. In fact, the physical properties of the steel depend on the temperature, but here we will simulate a simplified case and take some average constant values just to demonstrate you the basic principles of building the induction heating models. The induction heating model consists of two problems, magnetic and thermal. In magnetic problem, we calculate the eddy current density distribution in the body and the corresponding Joule heat power loss in the body. In thermal problem, we specify the Joule heat power loss and specify the cooling conditions and calculate the temperature distribution. Okay, let's start QuickField now and begin the simulation. In QuickField, I create new problem. Magnetic. Next. Problem type is AC magnetics. Frequency is 22 kHz. Model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem tree, and on the right is the geometry model editor window. You should draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it here from scratch. First, I'm going to insert a circle with a diameter of 8 millimeters. Insert, and another circle with a diameter of 6 millimeters. Insert, close, zoom to fit. This is the hollow conductor. Okay, switch to select objects mode, click the conduction to select, right click, move selection, displacement by 33 millimeters up. And I need another conductor, right click, duplicate selection, displacement by 18 millimeters to the right, and I need one copy more. Next, I'm going to insert another shape, a rectangle, with the dimensions 100 by 50 millimeters, and the insert point will be here. Insert. And I need another rectangle with the dimensions 100 by 30 millimeters. Insert, close, zoom to fit. This is the steel tube, this is the inductor. In axisymmetric problems, the horizontal axis is the axis of rotation. We should draw only the upper half of the cross section, so I switch to insert mode, draw the line here, switch to select objects mode, click the object to select and remove it. Delete, and I should delete this edge and this edge. In fact, the magnetic field is distributed not only in the inductor and the tube, it is distributed in the surrounding air, so I need to add the air block to the model. To add a block, I should draw the block boundaries. Zoom out, switch to insert mode, and draw the line. Change the line type to the half arc, and draw the arc here. Switch to select mode. This would be the air block, and this one would be the air block. Let's assign labels. Through labels we can distinguish geometric objects and provide physical properties. Switch to select objects mode, click the object to select and type in the label name here. Air. Click this one. This is air. Let's zoom in. Switch the zooming mode off. This is steel. These and these are water. To select multiple objects at the same time, hold the Ctrl button pressed. These and these are conductor. To be able to simulate the problem, we should define proper boundary conditions. QuickField automatically sets proper boundary condition on the axis of rotation, so we have to assign label to the arc boundary. Next, I should provide physical properties to the labels. Double-click the label name in the tree. The magnetic permeability of air is 1, and the magnetic permeability of water is 1. For the steel, I specify magnetic permeability of 400 and electrical conductivity of 5 megasiemens per meter. The voltage is 0. In axisymmetric problems, each block represents a cylinder with a gap. This is the block, and in 3D it is cylinder with a gap. In the gap you can put the voltage source or the current source. If you specify that the current is 0, that means there is indeed a gap here. If the voltage is 0, then it is a short connected ring. Exactly our case. So here in QuickField I specify that the voltage is 0. For the conductor, conductors are made of copper, so the permeability is 1, and the conductor carries the current 500 amperes. This is the root mean square value of the sinusoidal wave. In QuickField I should specify the magnitude, so I should multiply this value by the square root of 2. Conductors are connected in series. Okay. Far away from the inductor, the magnetic field fades to 0, so for the boundary I specify 0 magnetic potential. The last step before I can run the analysis is to build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution. Let's zoom in. The field picture should look nice. The field lines should be smooth curves. These lines do not look good. The solution that we have got is not accurate. You can use solve and refine to get a more accurate result. 5 refinement iterations, and I will not limit the mesh size, so I will type in 0 here. Okay. QuickField automatically refines the mesh, calculates the results, and refines the mesh again. Now let's take a look at the results. Again, let's zoom in. Now the field lines look much better. You can adjust the field picture and choose the value to display, for example the Joule heat value, and I will switch off the field lines. What else can you get apart from the nice picture? You can get some numerical values. You can use the contour tool, click the block to select, follow to the integrals, and calculate the total current value induced in the tube and the power loss, 2.3 kilowatts. In fact, the power is generated only in a thin layer next to the surface. Contour, remove contour. Let's zoom in. Switch to contour editing and draw the contour line here. Now for this line I open the XY plot. And on the XY plot you can see the power density distribution along the contour line. You see all the power is generated in a thin layer within 0.2 millimeters. The next step is to calculate the temperature distribution. To calculate the temperature distribution, I need to create another problem. Thermal. Next. Problem type is transient heat transfer, as I am going to simulate the temperature rise dynamics. Model class again is axisymmetric, length units are millimeters, and here let's pause for a moment. As you see, the Joule heat power distribution is not uniform, so we might expect to have hot surface and cold internals. QuickField allows you to export the power density distribution from magnetic to thermal problem. To be able to pass data from one problem to another, both problems should be based on the same geometry model file. The same means that here in the geometry model file, I should type in the file name that was used in magnetic problem. Alternatively, you can click Browse and search for the file. Here it is. Next, in transient problems, I should specify the time parameters. I'm going to simulate a 10 seconds heating process with the intermediate time step of 1 second, and the initial temperature is plus 25 degrees Celsius. Finish. The geometry model is the same and the labels are already assigned, but now I should provide thermal properties for these labels. I'm not going to calculate the temperature in the air, so for the air block, I do not specify any properties, just click OK, and you see the exclamation mark next to the label name. That means that this label is excluded from the analysis. I also exclude the water, and I'm not going to calculate the temperature in the conductor. I'm only interested in the temperature in the steel part. Thermal conductivity of steel is 20, density is 7800, and the specific heat is 420. As the power source will be imported from the magnetic problem, I do not specify any value here. Click OK. That's all for block labels. For the boundary, I do not specify any properties as well, because this label has no physical meaning in thermal problem. But I should specify the cooling condition for the tube, so I click to select the surface of the tube, hold the Ctrl button, press to select multiple objects at the same time, and assign new label, surface. And for this label, I specify the convection boundary condition. The ambient air temperature is plus 25 degrees Celsius and the convection coefficient is 5, and I specify the radiation boundary condition. Again, the air temperature is plus 25 and the emissivity coefficient is 0.5. OK. Now let's add the link to pass the data from magnetic to thermal problem. Open thermal problem properties, follow to the link step, data type generated heat, problem should be magnesium. OK. Browse. Here it is. Open. Add the link. OK. Now we have created the link. The generated heat from magnetic problem will be passed to the thermal problem. Now let's solve thermal problem. And we've got an error message. The linked problem results are out of date. The linked problem is this one, the magnetic problem. Why are the results out of date? That's because we have modified the geometry model. Remember, both problems share the same geometry model file. We have assigned a label to the surface of the tube, and we have provided physical properties for this label in thermal problem. But we should also provide physical properties for this label in magnetic problem. In fact, this label has no physical meaning in magnetic problem, so for this label I don't provide any physical properties. Just click OK and you see the 0 mark next to the label name. This mark means that this label doesn't affect the results. Anyway, the geometry model has been modified and the data file has been modified, so we have to solve the problem again. Solve the problem. You see, the geometry model was modified and the data file was modified. Let's open the results. Let's verify the results. I will click the block to select and calculate the total power. The same value. So now let's solve thermal problem. Solve. Let's take a look at the results. Here you can see the temperature distribution in the tube after 10 seconds of heating. Initially it was 25, then the temperature changed with time. You can use a contour tool here as well to get, for example, the temperature distribution along the contour line in this cross section. Open the XY plot. This is the temperature of the external surface, and this is the temperature of the internal surface of the tube. And here you can see how this dependency changed in time. Okay, we have simulated the model with simplified physics. In fact, the properties of steel depend on temperature. You can specify thermal conductivity as a function of temperature. You can specify the specific heat as a function of temperature. And you can specify the electrical conductivity as a function of temperature. And you can pass the temperature distribution from thermal problem to magnetic problem and get the corresponding non-uniform electrical conductivity distribution. But this is an advanced topic that we will discuss in other videos. If you search for the copper inductor steel tube on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. The simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.